Howdy, everyone. I hope you're all doing well. In this presentation, I'll be covering two topics that hopefully you'll find interesting and useful as you work on your research assignment that is due, I believe, next Wednesday. First, we'll go over the concept of resilience, exploring how it applies to engineering and more specifically to process design. Then we will discuss and talk about industrial symbiosis, what it means, and how resilience plays a crucial role in its implementation and success. So it is inevitable that we will always have disasters, be that hurricanes, floodings, freeze, and from charts like the one I'm showing here uh, by the National Centers for Environmental Information, what's clear is that these disasters are not only becoming more frequent, but also more costly over time. And this is largely driven by a combination of factors, population growth, urban developments in highly vulnerable areas, uh, but also climate change, because climate change intensifies these extreme events. And given that our focus is on the industrial processes and the impact of disruptions, if you consider a region like the Gulf Coast, which is home to numerous industrial and manufacturing facilities, I mean, this is home to close to 50% of total petroleum refining capacities, as well as 50% of the total natural gas processing plant capacities. The reported economic losses exceed $500 billion, but it doesn't really capture the full extent of devastation when it comes to the environment and to the society. Now, these disruptions are always going to happen one way or the other. And the primary reason is because how interconnected and interdependent our world and industries are. So something happening in a distant part of the world will ripple and find its way to your city or business or industry in general. Now, these interdependencies have been studied extensively, specifically in the critical infrastructure domain, and this is where I borrowed the chart you see on the right. Uh, and they are mainly categorized into physical interdependencies. So you can think about the material exchange between two entities or two facilities. So you have like, for instance, in the chart, you can see a natural gas supplying a power plant with fuel for generators. There's cyber interdependencies. These anything that involves the exchange of information. You can also think about geographical interdependency. So maybe there's no physical or cyber interdependency, but there's a proximity of system. So you can think, which will lead me to the fourth category, which is logical interdependencies. You can infer a relationship. So you can be in a country where some regulatory or policy changes affect a neighboring country, and this delayed impact of regulations and policies on industries take years to materialize, and basically disruptions that arise from these interdependencies can take many forms and can be classified in terms of source and magnitude. And by source, we mean, is it from within your system? Is it an internal disruption, or is it an external disruption? And also, it can be classified in terms of magnitude, so how large or small the disruption is. Keeping in mind that a very small disruptive event can cascade and causes larger disruptions that can propagate through the system and affect not only your overall system, but also other systems that depend on your process or on your system basically functioning well. So resilience, which is a concept and can be described as a property of systems, is really multifaceted and multidisciplinary. So you can look at it from an etymology perspective. You can also look at it from a modern usage perspective, which usually has resilience defined as the ability to cope with stress. But you'll find different definitions depending on the context or discipline that you're examining. And resilience theory seeks to give a unified framework. However, the concept is deemed by many as somewhat abstract, elusive, ambiguous, and because it depends on the system itself, like the system ontology depends on the how you define the system boundaries. Does your system have the ability to self-organize? So it makes it really hard to give one universal definition. However, one of the important things in the resilience literature is that it is visually represented through what is known as a bathtub curve. In the bathtub curve, you have the x-axis as time, and on the y-axis you have some performance metric that reflects the overall health of your system or something you're interested in measuring, be that a production capacity or maybe revenue from sales. So you can imagine your process or system is working as intended, and then something bad happens which causes your system to fail partially. And you can think about this disruption as, for instance, a major equipment failure. Then naturally, there will be a response from the operational team to restore the process, and this will take time until the process is returned to normal operation. Now, the dip or depth of this bathtub highlights how resilient your overall system is. Now, of course, it's not necessary to restore the performance to the original one, so it can be a repurposed performance that could be higher or lower than the original one, and also it can be allowed to fail safely if that's the case. So you can categorize phases around this disruptive event into three phases. You can look at a pre-disruption phase, and then you have a post-disruption phase, and then you have whatever is in between phase. This is where your operation is not working as planned due to whatever disruptive event that has happened. So the bathtub curve is a great way to see or to show the life cycle of a system. So going back to what is meant by resilience, you'll find many definitions phrased differently. And also in chemical engineering, specifically in 1982, the term resilience was defined in the context of control systems in terms of attributes such as operability, controllability, and flexibility, which also require definitions themselves depending on different contexts. However, many of the definitions really converge on 3 or 4 core capacities or main capacities, depending how the system boundaries are defined. And the 4 or 3 main capacities are an anticipatory capacity, an absorptive capacity, an adaptive capacity, and a restorative capacity. So if you look at the bathtub curve, we can see these capacities during the different phases. So we can see in the pre-disruption phase, we can anticipate potential upsets. This can be early on during the conceptual design phase or during a retrofit phase. What this really means is that in this phase, we can be proactive and have proactive strategies to prepare for potential disruptions. Then when a disruptive event happens, the system should not fail immediately. In other words, it should absorb shocks. Then it should be controllable and can adapt to the changing conditions. Now, in these two phases, you can also employ a concurrent resilience strategies that focus on maintaining functionality during the disruption phase. Then, reactive strategies are implemented in the post-disruption phase to restore the system to a stable state. So now that we know a little bit about resilience, how do we include it in the design of industrial processes, whether during the conceptual design phase or during the retrofitting phase? Noting that the inclusion of resilience is really most impactful when addressed early on, where you have more degrees of freedom, as compared to the retrofitting phase, where technical difficulties along with financial ones usually arise. So this way of thinking, including resilience early on, parallels the concept of inherently safer design, where safety is considered from the outset. Now, some of the charts that I've shown till now are borrowed from Dr. Al-Hawagi's paper, in which he suggested 12 disaster resilience principle strategies to enhance the resilience of manufacturing facilities. I have it on the last slide under suggested readings, but you can see the 12 strategies here, and you'll find more details and examples when you go through the paper, which I encourage you to do so. So to take one example, let's look at the repurposability strategy, where it simply refers to the capability of a process to be repurposed to produce different products or products that are different from the original intended ones. So you can look at, for instance, the block flow diagram that shows natural gas and oxygen being used to synthesize methanol. Now, as many of you witnessed during the pandemic, the demand for hand sanitizers went up the roof. And one question that may come to mind, can methanol be used in some way to manufacture hand sanitizers? Well, the answer is yes, but how? So the process of methanol can be repurposed given certain requirements or constraints being met to produce ethanol, which can be used to manufacture hand sanitizers. So if you look at the second block flow diagram, where the process is almost identical, except for the apparent change in catalyst. Of course, there will be changes in terms of vessel capacities and some other design parameters, but 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 the idea that the methanol process may be repurposed to produce a different product is worth considering during the conceptual design phase, where one of the steps is usually looking at the different processes and evaluating them. So being resilient aware will highlight such process. You can also see an example that actually has happened back in 2020, where some wine and beer distilleries repurposed their process to manufacture hand sanitizers for their local communities. So we talked about resilience, what it is, and we highlighted that it's important to be aware of disruptions that arise from the unavoidable interdependencies, and how important it is to include resilience in the conceptual design phase, and just being resilient aware. One interesting example is industrial symbiosis, that from the name it draws inspiration from nature, like many other innovations. And just to refresh your memory, symbiosis is basically any beneficial mutualistic relationship between two entities. And one example of mutualistic symbiosis can be seen between this oxpecker and the impala, where the oxpecker feeds on parasites and ticks that are found on the impala, and while simultaneously improving the impala's health because these ticks and parasites uh, feed on its blood, which will make its health deteriorate if it weren't for this oxpecker. So this relationship is mirrored in the industry where you have separate entities that engage in a collective approach through the exchange of materials, energy, water, and byproducts. And you can see this example in one of the well-known industrial symbiosis networks, which is also termed as eco-industrial parks in Denmark. And you can see an example of the industries involved in the specific eco-industrial parks and the type of exchanges they engage in. And you can find similar examples that can be found across the globe, including in the United States here, and South Korea, China, and various parts of Europe. And you'll find uh, eco-industrial parks or generally industrial symbiosis network that have more than a thousand facility that exchange products of all sorts. Here you can see an example of an intriguing conceptual model for industrial symbiosis network. That is the carbon, hydrogen, oxygen symbiosis network. And as the name suggests, the exchange components primarily contain carbon, hydrogen, and oxygen. And what sets this model apart is its introduction of an interception network, which includes interceptor units. Now, these units go beyond simple material exchange found in the many existing eco-industrial parks or industrial symbiosis networks. It goes beyond it by transforming, mixing, and separating components to meet the specific demands of participating facilities. So, for instance, if a plant requires methanol and none of the other facilities can supply it directly, then an interceptor unit, such as the methanol synthesis unit, can produce it to fulfill the need. And all industrial symbiosis network exemplified by the existing industrial parks or eco-industrial parks are driven by profitability, like any other business or industry. However, this is achieved by sharing an infrastructure that allows maximizing resource efficiency or resource utilization, while reducing environmental impact and delivering societal benefits. So this idea of co-locating and maximizing resource utilization for economic advantages is appealing. However, it does come with a cost of being highly dependent on other participants to operate. In this chart I'm showing, you can see the industrial symbiosis literature categorized by theme and country. And you can note that the research, or you can notice that research has focused on the synthesis, modeling, planning, and the social aspects of the industrial symbiosis. However, resilience has received comparatively less attention. Now, the reason I took this detour to discuss industrial symbiosis is that I really find it both like it's fascinating, and also it's a microcosmic representation of this global interconnectedness that we live in. So it's like a condensed model of how the world's interconnections basically function. You can see the effects ripple through the systems at a much faster rate. Also, part of my reasons is that this is what I worked on during my master's thesis, which we will see on the next slide. So the case study is to examine the resilience of a carbon-hydrogen-oxygen symbiosis network, which was synthesized based on economic metrics. But the overall framework can include any type of network that can be represented in a node arc representation, which is all what networks reduce to. So you either you start with an existing network implementation, or you use targeting techniques or mathematical programming. Two techniques actually that are covered, I think, on chapter 11 of Dr. Hawaii's book. So you use targeting techniques or mathematical programming to synthesize a network based on a postulated set of available resources and desired targets. Then the synthesized network will consist of nodes and will consist of arcs. The nodes represent facilities and plants. The transportation arcs can represent streams, for instance, or shipping routes. Then after doing so, we assign a degree of dependence between two nodes, which is basically a percentage that show how a receiving node's output is affected by a disruption on the sender's node. So in other words, if node A gives node B 1,000 units of something and node B is 10% dependent on node A, then node B's output will be reduced by 10%. And you can see the propagation mechanism in the top right corner. Then after assigning the degree of dependence, we choose an appropriate performance metric that reflects the overall health of the system, like we discussed before when we were talking about the bathtub curve. So something like a revenue sale or production capacity, something that you can establish what a normal operation looks like in terms of performance. Then in disruption modeling, each node in the network is disrupted individually, and then we see the effects after the disruption happens. In other words, after the failure is propagated through the network, and then we can identify the critical nodes and arcs. The last step in terms of assessment is postulating different recovery strategies so that we can calculate resilience. And you can see the bathtub curve recreated in the plot I'm showing. And you can also see how resilience is calculated, which is by taking the area under the curve pre and post disruption. Now, of course, after doing so, if the result is satisfactory, in other words, you deem the network to be sufficiently resilient, then there are other trade-offs you can consider. You can make the analysis more rigorous, and you can enhance the overall analysis. If the network is not resilient, then you can go back and refine, for instance, the synthesis formulation. So we talked about how we synthesize the network in targeting techniques or mathematical programming. You can choose different metrics other than the economic metric. You can choose something that reflects resilience, if you can express it mathematically. And you can synthesize new networks, and then you can examine the resilience, or you can revise the degree of dependence that you assign between the nodes. So here we can see the problem statement. We basically have several plants located within the same industrial parks. They have some internal sources they want to exchange, and they also utilize external sources. We know the commodity being transported, the associated flow rates, and the degree of dependence of each facility on the incoming stream. We want to know or assess the resilience of the network. So starting with a postulated set of industrial plants that have internal sources that are available for integration, and also some requirements, meaning components they need to operate. So we have a power plant, a steel plant, we have a gas to liquid plant, an ethylene production plant, dimethyl ether plant, and methanol to propylene plant. And what's in red is basically the sink requirements, and what's in black is the internal sources that are available for integration, and all of them are in kmols per hour. Then we synthesized a network based on targeting techniques. And you can see the original set of plants, but you also see a separation and mixing hub and also interceptor units. In our case, a methanol synthesis unit, a steam reforming unit, and a water gas shift reaction unit. Then, so now we know the sending and receiving nodes. We know the type of commodity. We can assign a degree of dependence based on different factors. And what's going to happen now is that each node is going to be disrupted. Failure will propagate. The effects will be calculated, and then we can identify which nodes are more critical than others. So looking at this two plots, we can see the nodes on the left-hand side or on the left chart, and the right chart shows the arcs. And it shows which nodes are most critical than others. And in our case, we can, for instance, see that the ethylene production plant and the natural gas supply stream are the critical node and arc respectively. So after identifying a critical node or a critical arc, we can postulate different recovery strategies, and we can see three different set of outcomes in which resilience is highly reduced with more more delayed response. And what this analysis really serves as is a preliminary view of worst case scenario, and it doesn't address the nature of the disruption. In other words, we're being agnostic about it. However, it allows to further look into or zoom in a specific to a specific in a specific into a specific critical node. So in this case, the ethylene production plant, and if you go through the literature and research, you'll find many common internal disruptions that cause major shutdowns, and then you can imagine. So, for instance, in the case of ethylene production plant, you have frequent malfunctions in the compression section. So you can imagine this ethylene plant being in a highly integrated, intensive network. Failure will propagate and will cause major economic losses, not only for the company that operates this ethylene plant, but also for the other participants. And I guess an important concluding remark is to always be resilient aware. And I mean, we're surrounded by uncertainty, not certainty. So try incorporating uncertainty and resilience into your framework so that you're always reasonably hedging against it, and you're able to bounce or spring back after upsets. In terms of suggested readings, I suggest going through the first two papers if you're interested in resilience. The third paper is good if you're if you want to know more about the existing eco-industrial parks internationally and the prospects of implementing some more in the United States. I know you have a lot to work on during these periods, so I really appreciate the time you took to view this video. And please get in touch with me if you're interested in discussing this further, or you want to ask a specific question, or would require, or you want extra resources. Thank you all for listening, and I wish you all the best.